Today we're going to be talking about spectroscopy, and we're going to be talking about specifically absorption spectroscopy that we do in the lab with our little Vernier instrument. And so I wanted to remind us of a few things. So we're going to be talking about the electromagnetic spectrum, and I wanted to remind us of just a few properties of electromagnetic radiation. Hopefully these are things you know, but let's think about it, right? Now we can describe light as a wave, right? We can describe it as a sine wave, and if we do that, right, the distance between two waves is the wavelength, right? And so this would be in some sort of distance unit, centimeters, nanometers, whatever, meters, depending on what kind of wave you have. And so, we can also look at, what's the amplitude of our wave that we're looking at. If we wanted to, we could calculate the, I can't spell today, frequency. And so the frequency, right, which is often given the symbol nu, is the number of oscillations per second. Right, and so in a vacuum, then the speed of light would be the wavelength times the frequency, and in a vacuum, right, C is equal to about 3 times 10 to the 8th meters per second. And so this is sort of the wave sort of theory, but we can also think of light, right, as energy. In this case, we think of light coming in, right, discrete packets, and we call those discrete packets photons. And we can talk about the energy of the photons. And so here we can talk about the energy of the photon, right, where E is equal to h nu, where h is Planck's constant. And so we kind of go back and forth between wavelength and energy as we talk about light. And so that leads us sort of to the concept, right, of the electromagnetic spectrum. And we're not going to do all of it today. I've put it up on the Colab site if you want to look at the sort of electromagnetic spectrum, right? But we can start with, if we start over here, we're going to start with the shortest wavelength, and that would be a gamma wave. Can't spell today. Gamma waves, and we would sort of move up from gamma to X-rays, and from X-rays you kind of get into the UV, and then the visible, and then the IR, and then the microwaves and radio waves are sort of out here. So again, wavelength is increasing as you go that way. But wavelength and energy are opposite things, and so the energy actually is increasing as you go this way. In our lab, we're going to be working with these little Vernier instruments. They're really visible spectrometers, not just UV spectrometers, and so it's interesting to pull out the visible. And it's useful to remind yourselves, right, that blue is the shortest wavelength, red is the highest wavelength. That means blue is the highest energy and red is the lowest energy. And you need that as we talk about absorption and fluorescence and that kind of thing. Okay, so let's remind ourselves of absorption spectroscopy. This is one thing I think you've done before in your first semester lab in this sequence. So it's good to kind of build on that. Basically, the concept of absorption spectroscopy is I pass some sort of electromagnetic radiation, i.e. light, through my sample, right? And I measure how much light or electromagnetic radiation comes out. And so this sample can absorb that light. Well, what light can it absorb, right? It can absorb, or how does it absorb, right? It absorbs by promoting electrons to a higher energy state. And so it does that only if the energy of the exciting photon exactly matches an energy gap or an energy difference in the molecule for an electron to go to an excited state. So if you just thought about one electron and its next state is so much energy above it, the photon coming in has to be match exactly that energy. Now the thing about a complex molecule, right, is there's a lot of electrons. And those electrons might have multiple different states that they can go to. And so that's why we end up getting peaks that are fairly broad. If we did atomic absorption, so we just looked like something like sodium, where you end up getting our very discrete peaks because there just aren't that many electrons, there aren't many states it can go to. But for molecular absorption, which is what we're going to do in this lab, we get broad peaks. And that's because there's lots of electrons and lots of different energy levels that they can go to. But each electron has to exactly match a photon in that area. And so the energy diagram might look something like this. This is going to be our ground state. On each ground state, we're going to have vibrational and rotational states. So these are just kind of directly above ground. To get to these, that would be sort of IR absorption. So we're not going to do IR in this class, but if you did an IR, but it's less energy, you just change the vibrational and rotational states. For UV vis, we get up to an electronic state. And so we have enough energy to promote it up to an excited electronic state. And these excited electronic states still have vibrational and rotational states. So this is an excited state. We'll call this the first excited state. There can be second excited states, etc., etc. If you put enough energy in, you might be able to get it up there as well. All right, so these are the first excited electronic states. And so again, if we would put in this amount of energy, we would get up there. But we could also hit it with a photon, right, with a little bit more energy, and we could get it up there, or we could get it up there, etc., etc. So now you see why a molecule with all these different vibrational and rotational states can absorb a variety of different wavelengths that are passing through. So what's the molecular orbitals that translate into these? We've kind of looked at the energy diagram, but we need to think about molecular orbitals for a minute. And so remember back to bonding, you can have a single bond, right? You can also, right, have a double bond, and then we're going to talk about electrons that are like non-bonding. So, right, if like for instance, if you have oxygen that's bound to like carbon, right? One of these is actually a sigma bond. The second one is a pi bond, and the oxygen has two lone pairs, right? And so these, right, would be your non-bonding electrons. So those are the types of bonds that we can have. And remember, for all the bonds, we also have an anti-bonding state. That's a higher energy anti-bonding state. Don't have an N star because there's no anti-bonding if you're not bonding, right? So you can only have an anti-bonding if you're bonding. And so the energy, this is energy, goes up as we go from here. So let's think about starting at a sigma, just a single bond, right? And going, where can we go? Well, we can go from sigma to sigma star, or we could go from sigma, right, up there. We can go, actually, it's hard to go from sigma to pi star. I'm going to leave that one in there. It's easy to go from pi to pi star. It's also easy to go from n to pi star, and you can actually go from n to sigma star as well. It's hard to switch between the sigma and the pi's, so we didn't connect those two. But not all of these are sort of equal. It turns out that the n to pi star, and especially the pi to pi star, are the best ones to look at. So it turns out the energy difference to go from the sigma to the sigma star, oops, I drew these wrong. Turns out the sigma star is actually higher in energy. Let me correct my diagram. Let's do it again. Make sure I get these. The pi ones don't matter so much. So the sigma star one, that's why it's so difficult. Sigma to sigma star is a lot of energy, whereas pi to pi star is not so much. So a lot of energy means we have to have a shorter wavelength, right? Shorter wavelength. So if we really wanted to do sigma to sigma star, this is really in the deep UV region. It's also not particularly useful. And that is because every molecule has sigma to sigma star transactions, right? Everything has like single bonds. And so you got to have a lot of energy, and so it's not particularly useful. Pi to pi star, on the other hand, is the one that's most useful. And so where do we have a lot of pi orbitals? Well, I already said it, right? Double bonds. So a lot of times people will say that UV vis absorption is a general technique, and I like to put a caveat. It's a general technique for things with double bonds. If you don't have any double bonds, it's really hard to use it to detect your molecule. So everything we're going to look at has double bonds. These ones just turn to absorb better, but if you have n to pi star, they will absorb. They just absorb less. And so what is that absorption thing? We call this epsilon molar absorptivity. And so molar absorptivity is usually in this funky unit of liters per mole centimeter. So the higher the molar absorptivity, the more it absorbs. And quite frankly, the more double bonds, the higher the molar absorptivity. So if there's one thing you get out of this, double bonds, double bonds, double bonds, that's what you want for UV vis. Okay, so let's think about calculations then. Again, I'm assuming kind of everybody remembers Beer's law, but we'll do it real fast. Right. Beer's law comes from that diagram I showed you. We have some sort of power that's coming in. We'll call that our initial power. We get some sort of power out. Should be smaller than the power in. And we have an absorbing solution of concentration, and this light is passing across some distance, B. Right, and so the absorbance, so the transmittance, right, is the power out of the power in. And absorbance ends up being minus log of the transmittance. So minus the log of the transmittance gets you there. And so it puts a log in there. And so right then we get to Beer's law, which says, right, absorbance is equal to molar absorptivity times the path length times the concentration. Again, we defined B up here as the path length, the distance that it has to go across. So what do you do then to maximize your absorbance, right? Well, obviously you want to pick a compound that has a high molar absorptivity. A higher concentration is going to give you more absorbance, and you want actually to think about path length. We'll talk a little bit when we talk about detectors. We use a UV detector on the HPLC, and the problem with the HPLC, right, is that you actually have to think about path length. They actually design cells to think about path length in this. So Beer's law comes up in other places, not just little spectrometers, but you'll see it in the HPLC section as well. Of course, there's problems sometimes with like light losses, right? Like light can be reflecting. And so to get around losses, right, the best way to do that is to run a blank. And so we put our cuvette in, we put it in with our solvent, we want to see how much light we're going to lose. We'll subtract out any of that, and so we'll be able to come back around. And so absorbance is just a really quick and easy way to pull out concentration values. And we'll be looking at that today to look at concentrations in the lab.